Hi, in this video we're going to do something called partial fraction decomposition. We're going to take a rational function, which are polynomials divided by polynomials. Remember, those are called rational functions from pre-calculus class. And we're going to break it down into smaller pieces with this thing called partial fraction decomposition. That's what the word means, is we decompose it into smaller fractions that are more manageable. That's the basic idea. It's better if we just get started. Partial fraction decomposition is used in order to take the antiderivative of rational functions, polynomials divided by polynomials. I'm going to start with a quick example of something that you can take the antiderivative of without partial fractions. Remember that a constant by itself is like a polynomial of 0 degree. So 1 is a polynomial, and 2x plus 1 is also a polynomial. So this is a rational function, and we're going to take the antiderivative. This one is a standard substitution problem with u equals 2x plus 1. Then our du is 2 times dx. I get 1 over u times a half du. Pull the half out, and this is a completely reasonable problem. And there's our answer for that problem. Now, for a second example, we're actually going to do partial fraction decomposition. This time, the reason why substitution is not going to work is because the denominator is going to be squared, and the numerator is just a 1. So if you try out substitution with u equals x squared minus 9, what you'll find is that the du, or the 2x dx, does not appear in this problem. There's no extra x that can be part of the du. So substitution doesn't work on this problem. The first step of partial fraction decomposition is to fully factor the denominator. After the denominator is fully factored, we're going to do some algebra. And this is the partial fraction decomposition part of the problem. This fully factored version of the problem can actually be written as a number over x plus 3 plus another number over x minus 3. And all we have to do here is figure out what capital A and capital B should be. We're going to get a common denominator on the right side of the equation. The first term I'm multiplying x minus 3 over x minus 3, and the second term I'm multiplying x plus 3 over x plus 3. Now what happens here is that after I get a common denominator, now the denominator on the left side of the equation is the exact same thing as the denominator on the right side of the equation. So they cancel out. And here's what we're left with. 1 is equal to a times x minus 3 plus b times x plus 3. There's a couple of different ways of solving for a and b at this point. The way I'm going to do it is to use the following concept. This equation is supposed to be valid for all possible x values. What that means is that we're allowed to freely choose any x value that's convenient for us in order to solve for a and b. So let's, in this equation, set x equal to 3. What does that give us? It gives us 1 is equal to a times 0 plus b times 6. And then I get b is equal to 1/6. In order to find the a value, setting x equal to minus 3, I get 1 equals a times minus 6 plus b times 0. And I get a is equal to negative 1/6. Now all of that was just a side computation. Let's get back to the original problem. This quantity of 1 over x plus 3, x minus 3 can be written as the a value over x plus 3 plus the b value over x minus 3. Now that I know what a and b are, I can proceed with the antiderivative, pulling out the constants, using the properties of integrals. Now these are simple problems. Feel free here to do out the substitution with u equals x plus 3. And for this one, a separate substitution with u equals x minus 3. What you get after you do that work is the ln of x plus 3 and the ln of x minus 3. There we go. That's our problem. Don't forget plus c. Here's our next problem. But the first step for every single partial fraction decomposition problem is to fully factor the denominator. So let's start with that. Pulling an x out, I'm left with x squared plus 16. And now the question is, are you sure that you can't factor that anymore? Remember that anytime you factor a polynomial, those factored pieces will tell you when the polynomial is equal to 0. But x squared plus 16 is never equal to 0. So x squared squared plus 16 is not factorable. Another way to think about this is using the quadratic formula. So let's just try the quadratic formula and see what happens. Here in the quadratic formula, my a is equal to 1, my b is equal to 0 because there is no x term, and my c is equal to 16. Now look at what's happening underneath the square root here. Square root of negative 64. X squared plus 16 is not factorable because when you do the quadratic formula, the stuff under the square root is negative. So keep that in mind for future problems, because for partial fraction decomposition, if you don't fully factor the denominator, if that messes up the whole problem. So you have to make sure you factor until you can't factor anymore, and if you're not factoring something, better be because it's strictly not factorable, because the quadratic formula gives the square root of a negative number. Now that we're sure that this is fully factored, we can go ahead and do the algebra for our partial fraction decomposition. So part of what I want to show you here in this example is how to do the setup for the partial fraction decomposition. When the integrand is fully factored, what you do is you take each one of these factors, and the setup is going to give one term to each of these factors. X goes here, and x squared plus 16 goes here. And then what's going to happen is that the numerator has to be one less degree than the denominator. X is a first degree polynomial, so I need a 0 degree polynomial on the top, or a constant. X squared plus 16 is a second degree polynomial, so I need a first degree polynomial on the top. So I'll go with bx plus c, where b and c are constants. The algebra is exactly the same as it was on the previous slide. First, we have to get a common denominator on the right side of the equation. This first fraction is going to get multiplied times x squared plus 16 over x squared plus 16. And this second fraction is going to get multiplied times x over x. Now we've got the same denominator appearing on the left and the right. This will happen in every single partial fraction decomposition problem. If it doesn't happen, then you did something wrong. Because these are the same, they can cancel out, and we're left with just the numerator equation. Now, like I said in the previous example, there's a couple of different ways that you can solve for ABC here. You can actually do this problem by setting x equal to a couple of different values and trying to figure out what ABC is from there. I want to show you a second method that works as well, which is to gather everything on the right-hand side into powers of x. Here's what I get, and now let's collect powers of x, collect coefficients. Now, the way this strategy works is that once you've collected the coefficients, you can set the coefficients equal on opposite sides of the equation. So on the right, there's a second degree polynomial here, and on the left, it doesn't look like it because 8 is just a constant by itself, but the left-hand side can also be a second degree polynomial if I add 0 times x squared plus 0 times x. Now, the only way that a polynomial could be equal to a polynomial is if the coefficients are equal. If the coefficient of x squared is equal to the coefficient of x squared. So I get a plus b is equal to 0. And now the coefficient of x should be equal to the coefficient of x. C is equal to 0. And finally, the constant term should be equal to the constant term. 16a is equal to 8. So this is 3 equations and 3 unknowns. This one is telling us that a is equal to a half. Obviously, c is equal to 0. That one's pretty clear. And this one, if a is equal to half, then b is equal to negative half. Okay, so we've got our desired values for a, b, and c. Now we need to get back to the integration. Remember, what we found in the previous slide is that this a value is a half, and this c value is 0, and the b value is negative half. Now we can actually take the antiderivative of this. Simplify, use properties of integrals in order to move things around and make the problem easier for yourself. The first one of 1 over x, the antiderivative is ln. This integral should be done with u equals x squared plus 16. I know at this point in the course you are qualified to do that substitution, so I trust that you can do this on your own. And I'm just going to jump to the answer. You get a half that comes from the substitution and ln of x squared plus 16. There we go. That's the answer to the problem. Now let's review the rules for partial fraction decomposition setup that we've learned so far. The first rule is to fully factor the denominator. The second is that when you set up the partial fraction decomposition, the degree of the numerator should be 1 less than the degree of the denominator. And finally, there is one more rule that we haven't covered so far, which is for repeated factors. The last rule says if there are repeated factors in the denominator, then the setup has to also repeat that factor as many times as it appears in the denominator of the original problem. It's really better if I just show you an example. The first step is to fully factor the denominator. And this is where we get into the repeated factor rule. This x is appearing 2 times because it's squared. There's going to be one term for x, which is the base factor, and then another term for the x squared because it's repeated. And then the x plus 1 also has to appear, but that guy's not repeated, so it's just a regular term. And if you look through the book and all of the rules that are listed in the book, you'll see that if this was raised to the 5th power, I would need 5 of these terms, x and x squared and x cubed and x to the 4th and x to the 5th, right? The first 2 terms here have a first-degree polynomial in the denominator. I know it kind of looks like x squared is a second-degree polynomial, but that's the tricky thing about the repeated roots. This is really first-degree polynomial of just x, but it's repeated 2 times. So the numerators of these should be a 0-degree polynomial and a 0-degree polynomial, just constants, because both of these terms come from the first-degree factor of x. Okay, and then the last term, the denominator's first degree, so the numerator should be a 0th degree polynomial or a constant, which is c here. The algebra proceeds as usual. We should get a common denominator, and our goal is to solve for a, b, and c. And so I get my numerator of 1 is equal to the numerator on the right side. Now let's continue with this algebra. Using the strategy from example 1, notice that if we set x equal to 0 in this equation, a bunch of stuff cancels out, and I find out that b is equal to 1. Now let's try setting x equal to -1, and I find that c is equal to 1. Unfortunately, we ran out of x values that will make stuff equal to 0. So let's just pick something else that seems reasonable. How about x equals +1? Let's see what happens. And what I'll do that's slightly different in this last one, because things will not be just canceling out easily, is actually use my b value that I found here and actually use my c value and also set x equal to 1. So let's see what we get. And let's just simplify. A is equal to -1. Okay, so those are my 3 values for the constants. And as usual, we're going to use this result in order to actually integrate the problem. The first gives me -ln of x. This next one, this is like x to the -2 power, and I should apply the power rule. And the final term on the end is ln of absolute value of x plus 1. And there's our answer for the problem. So I hope you enjoyed this video on partial fraction decomposition. As you can see, following the rules, knowing the rules is really important for partial fraction decomposition. So review that stuff before coming to class. Make sure that you have that list of the rules for partial fraction decomposition before you come to class. So I recommend that you look it over a couple more times before you come to class and go ahead and try your homework problems early. We'll see you soon.